Imagine you're sitting at your desk, right? You're working on this massive project, and you finally hit that button to run a calculation. Or maybe you're rendering a video.
Oh, yeah. We're compiling code, the
Yeah.
classic waiting game.
Exactly. You lean back, and you're just waiting for that satisfying little ding that tells you the job is done. But the ding never comes.
Never comes.
Right. Instead, your mouse cursor just turns into that spinning beach ball of death.
The universal symbol for, something has gone terribly, terribly wrong.
Yeah, and the fan on your laptop starts sounding like a jet engine taking off. The progress bar just freezes at like 99%.
Which is almost worse than freezing at 1%, honestly.
It is. It's agonizing. And what do you do in that situation? You feel this spike of frustration, you hit force quit, and you just assume the program is broken.
Right. You assume it fell into an infinite loop, it crashed.
Uh-huh.
Because to our modern engineering mindset, a computer program is just a tool, right? It's supposed to give us a clean, precise, finished answer.
Right.
And when it just keeps spinning forever, we consider it a complete failure, a dead end.
But what if I told you that by force quitting that program, you might actually be killing this, like, deeply profound mathematical journey?
Oh, wow. Okay, setting the stakes high.
I mean it.
Yeah.
What if that infinite loop isn't actually broken at all? What if it's tracing a hidden, perfectly rigorous mathematical shape, and the only reason you can't see the value is because you're using the wrong kind of clock to observe it?
Okay, that is a massive paradigm shift. I mean, you're taking the literal definition of a computational failure and claiming it has a hidden architecture.
Yes.
And historically, that idea hasn't just been ignored by mathematicians, it's been actively feared.
Feared is almost an understatement, honestly. So, welcome to the deep dive. We have this fascinating stack of source material today centered around this paper called Asymptotically Fair-Stopping and Divergent Computation.
It's a dense title, but a totally wild concept.
Super wild. And to ground us, I want to start with some history before we get into the actual physics of computation. The authors highlight just how terrified the giants of mathematics used to be of these infinite, non-halting processes.
Terrified is the right word.
Yeah. There's this quote from the Norwegian mathematician Niels Henrik Abel, and he wrote this back in 1826. He literally complained in writing, mind you, that divergent series are an invention of the devil.
An invention of the devil. You really have to appreciate the dramatic flair of 19th century mathematicians.
Right. They took this stuff so personally. Abel wrote that it was a total shame to base any mathematical demonstration on these infinite series because they were basically fallacies.
Well, depending on how you group the numbers, you can manipulate a divergent series to spit out whatever paradoxical answer you want.
Exactly. He saw them as a source of total mathematical anarchy.
Which, to be fair to Abel, was a completely valid anxiety at the time. I mean, in 1826, mathematics was desperately trying to become this rigorous lockdown discipline.
Right, they wanted hard proofs.
Absolute limits. A series of numbers that just explodes toward infinity or violently oscillates forever without ever settling down. That felt like a structural threat to the logic they were building.
But then you contrast Abel's dread with a letter written by Leonhard Euler. This is from way back in 1745. He's writing to his friend Christian Goldbach.
Oh, yeah, this is a great letter.
It's so good. Euler basically says, yes, these infinite series are wild, but my dear friend, if we do not find some way to tame these devils, we shall never compute the true shape of the infinite.
Compute the true shape of the infinite. I love that. Euler just had this incredible, almost physical instinct.
He really did.
He knew that the chaos of a divergent system wasn't just random noise. He suspected there's a foundational truth buried inside the explosion, even if the formal tools to extract it wouldn't be invented for centuries.
And that brings us to the actual mission of our deep dive today. This text we're exploring provides exactly those tools. It bridges that 18th century anxiety with modern computability theory.
Right, through this radical new framework.
Exactly. A framework built around something they call the STP operator, which is essentially a way of introducing a probabilistic observer into the machine.
And the claim here is that by introducing this specific kind of observer, you completely exorcise Abel's devils.
You turn infinite runaway chaos into stable, calculable physics.
It's amazing. But to really grasp how revolutionary this STP operator is, I think we first need to define the trap that classical computing is stuck in.
Okay, yes, let's build a mental model.
Right. We need to look at how a Turing machine, or even just a basic Python script on your laptop, actually moves through a calculation. Walk me through the classical view. What's actually happening under the hood when you hit run?
Okay, so at its most fundamental level, a computer program is a system that moves from one state to the next. So let's call the initial starting line state 0.
Okay, state 0.
The program reads this first instruction, it performs a tiny calculation, updates its memory, and boom, that moves it to state 1.
And then it just loops that process.
Exactly, it does it again. State 2. State 3, you can think of each state as the cumulative sum of all the little incremental updates it's made so far.
I like to visualize this physically, honestly.
Yeah.
Like, imagine you are walking through a dense city,
Yeah.
right? And you're trying to reach a specific destination.
Okay, I like this.
Every step you take changes your location coordinates. That exact location you're standing on, that's your state. And the little step forward is your incremental update.
Okay, so in the classical world, there are basically only two ways your walk through the city can end.
Right.
The first is the happy path.
The happy path. After a finite number of steps, maybe 100, maybe a billion, your instructions say, stop, you have arrived.
Right. You're standing exactly outside a cafe. Your journey halts.
We can measure exactly how long it took. We know your final coordinates, and the system outputs cafe. And everyone is happy.
The engineering requirement is met. We got our answer.
Exactly. But then there's the second scenario. What if your set of instructions has a flaw? Yeah. What if it accidentally tells you to walk around a single city block forever? Take a right, take a right, take a right, take a right.
Oh man, you just keep walking in that square until the end of time.
Or even worse, what if the instructions tell you to just walk straight down a road that has no end, just out into the desert?
In both of those cases, I never hit an instruction that says stop. I just keep walking.
Right. The program never halts. And because it never halts, classical discrete mathematics looks at your journey and basically says, there is no final destination. The limit does not exist.
Because there's no final state, the classical perspective just throws out the entire journey.
It says your walk has no value, no definable shape, and no measurable outcome. It's just trash.
But, and this is where the new framework pushes back, and honestly, it's where human intuition pushes back. Just because I never reached a final, tidy little cafe doesn't mean I was doing nothing.
No, of course not. You're physically moving.
Right. If I'm walking infinitely down a road or infinitely around a block, I am still somewhere at every single moment in time. I'm tracing a very real, tangible, dynamical path through space.
Exactly.
So why should we discard the reality of that path just because it doesn't fit into a neat little output box?
You're hitting on the core philosophical flaw of classical computability right there. It demands a static answer from a dynamic process.
Which is totally unfair to the process.
It is. If the system won't naturally settle into a static state, classical math just breaks down.
So if the program refuses to stop itself and we still want to measure the shape of its journey, we need an intervention. We have to be the ones to stop it.
Yes, we need an outside observer. And this is exactly where the STP operator enters the picture in our source text.
Okay, introduce the Exorcist.
The text argues that we shouldn't be asking what is the final state of this infinite program, because as we established, there isn't one. Instead, we should ask, what state do we expect to find this program in if we interrupt it?
Oh, okay. So I want to make sure I'm picturing this intervention correctly, because we aren't just saying, hey, let's pull the power cord at exactly 5:00 p.m.
No, that would be deterministic. We are introducing something stochastic, a random variable.
The text calls it tau, right?
Yes, the stopping time, denoted by the Greek letter tau. So we replace the absolute hard-coded end of the program with an independent probabilistic observer.
Okay.
This observer operates completely outside the logic of the code. It just watches the program run, and based on some probability law, it decides at a random moment to hit a giant red button that freezes the system.
So going back to our city block analogy, the program is walking around the block, and the observer is, like, standing on a balcony with a stopwatch and a pair of dice.
Oh, I love that image, yes.
And at a totally random step, based on a dice roll, the observer yells, freeze, and writes down exactly where the program is standing in that exact microsecond.
That is the exact mechanism. And the state that the program happens to be in at that frozen moment, let's call it state tau, that becomes our measured value.
But wait, I have to play devil's advocate here.
Do it.
If the stopping time is random, how on earth is this rigorous?
What do you mean?
Like, if I run the infinite program and my random observer stops it at step 10, I get one coordinate. But if you run the exact same program and your random observer stops it at step 10 million, you get a completely different coordinate.
True.
So how can we extract a stable mathematical truth from a totally random interruption?
That is the crucial pivot the framework makes. The answer of a divergent infinite program is no longer a single absolute terminal node. The answer is the expected value of the stop state across an infinite number of observations.
Okay, expected value. So we aren't just running this once.
Not at all.
We're imagining running this infinite loop trillions of times, letting our observer randomly freeze it according to its specific probability rules, writing down the coordinate every single time, and then averaging all of those frozen moments together.
That's the conceptual leap. We're looking for the macroscopic average of all those microscopic frozen states. The mathematical shape of the infinite path is defined by its expected value under observation.
But this feels like it opens up a huge loophole.
How so?
What if I design a terrible observer?
Okay, define terrible.
Like, what if I build an observer that is hard-coded to always yell freeze at exactly step 3, 100% probability? The expected value is just going to be wherever the program is on step 3.
Yeah, which tells you nothing.
Exactly. That tells me absolutely nothing about the infinite chaotic nature of the road ahead. I've just artificially frozen it at a local accident near the starting line.
And your pushback is precisely why this framework requires strict rules. You can't just use any arbitrary clock or observer to measure the infinite.
Right, because my step 3 observer is completely blind to the future.
Right. If we want to capture the true shape of the infinite journey, our observer must give the infinite tail of the computation a fair hearing.
And the text has a great phrase for this. They say the observer must be asymptotically fair.
Asymptotically fair.
I just love the philosophical weight of that. It's not just a mathematical operator. It's almost like a justice system for infinite numbers.
It really is. To qualify as an asymptotically fair observer, the probability law governing the stopping time has to pass two very specific conditions.
And it has to pass these tests as we push the observer to what they call the infinite horizon, right?
Exactly. Meaning, as the observer's tendency to wait grows larger and larger.
Let's unpack these two rules because they're basically the gatekeepers to taming the math here. Condition 1 is called tail exploration.
Tail exploration. This addresses your exact complaint about the step 3 observer. Tail exploration dictates that for any fixed number of steps, let's call it m, and let's imagine m is a massively large number, like a trillion.
Okay, a trillion steps.
The probability that our observer waits longer than a trillion steps before pushing the freeze button must approach 100% as we push our observer to the limit.
So, if I'm translating this into our physical walk, it means the observer must eventually be forced to completely ignore the messy, chaotic beginning of the journey. Right. The first trillion steps simply stop mattering. The observer is mathematically obligated to sample the deep, dark, infinite future of the computation.
That's the only way to ensure we're actually measuring the true divergent behavior and not just a startup sequence.
That makes perfect sense.
But condition 2 is where it gets really interesting, especially for systems that oscillate. Condition 2 is called spectral non-resonance.
Oh, I spent so much time thinking about this one because the intuition behind it is so physical. Let's go back to our program that's stuck walking around a city block.
The infinite square.
Right. Take a right, take a right, take a right, take a right. That path has a rhythm. It has a strict period. If you graph the coordinates, they just bounce back and forth in a repeating cycle.
It has a frequency. The algorithm has an internal clock rate.
Exactly.
Yeah.
Now imagine our random observer decides to check in on the program. But the observer's probability law has a hidden rhythm too. What if the observer only ever yells freeze on an even-numbered step? Step 2, 4, 6, 8.
Oh, you'd get a completely distorted view of the system.
Right. If it only looks on the even steps, it'll only ever see the program standing on the north and south corners of the block. It will literally never see the east and west corners.
The observer becomes blind to half of reality.
Yes. It reminds me of watching a video of a helicopter flying where the camera's frame rate matches the exact speed of the spinning rotor blades.
Oh, the Strobe effect.
Yeah. The blades look like they're standing perfectly still, bolted in place while the helicopter magically floats into the sky. It's an illusion.
That is the perfect physical parallel. In engineering, we call that aliasing. You're sampling the reality at a frequency that accidentally matches the system's own rhythm.
And when you do that, your observer phase locks with the program.
Exactly. You get an artificially stable, completely false picture of the dynamics. So how does condition 2 mathematically prevent that strobe light effect?
Well, it demands that the stopping probability distribution must be incredibly smooth and diffuse. Formally, it says that the difference in probability between stopping at step n and stopping at step m plus 1 must approach 0.
So no spikes, No gaps.
No hidden periodic rhythms in the observer's clock. It has to be like a completely smooth wash of light, so it can never be tricked by a program's internal strobe effect.
Okay, so tail exploration to see the deep future and spectral non-resonance to avoid the strobe effect. If an observer passes those two tests, it is officially an asymptotically fair observer.
And once we have established those rules, the text introduces the most fundamental, stripped-down observer we can possibly build. They call it the geometric STP law.
The geometric law. This is where we get to start testing things. How does this observer work?
It relies on the absolute simplest random process in the universe.
Yeah.
A memoryless coin flip. Imagine that at every single microsecond, at every single step of the computation, our observer flips a weighted coin. With a constant probability, which we'll call P, the coin lands on heads.
And if it's heads?
If it's heads, the observer slams the red button, the program is stopped, and we read the state.
And if the coin lands on tails?
With the probability of 1 minus P, the coin is tails, and the observer does absolutely nothing. The program is allowed to survive for one more step.
Oh.
And then at the very next step, the observer flips the exact same coin again.
So it's a constant hazard rate. The system is operating under this continuous, tiny thread of termination.
Exactly. This creates a geometric distribution for the stopping time. If you want to know the exact probability that the program gets stopped on, say, step 5, you have to calculate the probability that it survives step 1, survives step 2, survives step 3, survives step 4,
Right.
and then finally got hit by the stopping probability P on step 5.
Which mathematically means you multiply the survival chance 1 minus P by itself 4 times, and then multiply by P. It's a very elegant decaying curve of probability.
It is. Now, here is where the text makes a conceptual bridge that genuinely blew my mind.
I know exactly what you're going to bring up. Theorem E.
Yes. Theorem E, the geometric STP equivalence. We have this geometric observer, and we want to calculate the expected value of our computer program's final state under this observer. Walk me through what this theorem actually proves.
So Theorem E proves that the expected state found by our coin-flipping observer is mathematically identical to an ancient trick that classical mathematicians have been using for centuries.
Something called Abel damping?
Exactly.
Let's slow down here because this is the first massive aha moment of the text. Let's remind the listener what Abel damping actually is, because earlier we talked about Abel thinking divergent series were the devil.
Right.
But he, and others like him, did eventually figure out a way to force some of these explosive series to behave, right?
Yes, they did. When faced with an infinite series of numbers that was just blowing up, classical mathematicians would sometimes artificially multiply every single term in the series by a damping factor.
Like putting a louche on it?
Exactly. They'd multiply the 100th term by some variable x to the power of 100, where x is a number just barely smaller than 1.
So like 0.999.
Right. And because 0.999 to the power of a million is practically 0, this artificial damping factor forces the infinite tail of the series to shrink down to nothing.
It pinches off the explosion so the mathematicians can safely sum up the numbers.
But historically, that was viewed as a total G-code. It was a formal, abstract mathematical trick. You're artificially altering the numbers just to force an answer out of it. It didn't mean anything physically.
It was just a mathematical convenience.
Exactly. But Theorem E fundamentally rewrites the reality of that trick.
Explain how. Because when I read this proof, the way the algebra collapses is almost too perfect.
So let's visualize the structure of the math without getting bogged down in reading raw equations. To find the expected value, we have to sum up all the possible stop states, multiplied by the probability of stopping in each state. But remember, every state is itself a cumulative sum of all the little incremental updates the program has made.
So we have a sum of a sum. A giant nested pile of additions.
Yes. But because our coin flip probability P creates a nicely bounded system, the rules of calculus allow us to do a trick. We can rearrange the pile.
Okay.
Instead of looking at the stopping states, we can focus on the individual incremental updates. We can look at a specific update, say the increment at step 50, and ask, in all the infinite multiverses where this program is stopped, how often does the step 50 update actually get included in the final answer?
Well, it gets included if the program is stopped at step 50, or step 51, or step 52, or a billion.
Precisely. The step 50 increment is included in every single outcome where the program survives up to step 50. And when you sum up all those infinite stopping probabilities from step 50 onward, the math collapses beautifully. All the complex probability fractions cancel each other out, and you are left with just one clean term, 1 minus P raised to the power of 49.
Which is the exact mathematical definition of the survival probability.
Yes. And do you see what that means? The resulting formula for the expected state of our observed program is exactly the same formula as the classical Abel damped series.
The damping factor x is revealed to be 1 minus p.
It is a total paradigm shift. That mysterious damping factor that mathematicians thought was just an artificial trick to shrink the numbers. It isn't a trick at all.
It's a literal probability.
It is literally the physical survival probability of the computation. The series isn't being artificially shrunken by a mathematician's wand. It is being rigorously evaluated under the physical hazard of an outside observer.
That is just gorgeous. It takes this abstract manipulation and gives it a concrete computational reality. Abel's invention of the devil was just a computer program trying to run while dodging an observer's coin flips.
It really is beautiful. So now that we have this framework, we have to put it to the test.
Yes, let's look at some examples.
The text takes this geometric STP law and applies it to one of the most famously annoying infinite paths in math history, Grandi's series.
Oh, Grandi's series. It looks so simple, but it breaks everything.
It does. It's the bounded alternating path. The instructions for the program are just add 1, then subtract 1, then add 1, then subtract 1, forever.
Okay, so if we look at the state space, the running total of where the program is, what does it look like?
We'll start at 0. Add 1, the state is 1. Subtract 1, the state is 0. Add 1, it's 1. Subtract 1, it's 0.
The program just violently flickers back and forth. 1, 0, 1, 0.
It never escapes to infinity, but it never settles down. Classical limit does not exist.
But under our fair geometric observer, what is the expected state? Let's conceptually apply our coin flip. We want the average of all the states where the program might be stopped.
Well, half the time the program is sitting at 0. On step 2, step 4, step 6, the state is 0.
And anything multiplied by 0 is 0. So we can just completely sweep all the even-numbered steps off the table. They don't contribute to the expected value at all.
Exactly. The only states that add value to our expectation are the odd-numbered steps, where the program is sitting at a state of 1. So we just need to sum up the stopping probabilities for step 1, step 3, step 5, and so on.
We add up the geometric probabilities for the odd steps. And because it's a standard geometric series, skipping every other term, the algebra collapses into a very simple, tidy fraction.
It does. Without reciting the polynomial expansion, the infinite sum condenses down to a single expression. Exactly 1 divided by the quantity 2 minus p.
Okay, 1 over 2 minus p. This is where we have to invoke the first rule of being an asymptotically fair observer, tail exploration. We have to push our observer to the infinite horizon.
Right, we have to make the coin incredibly biased towards survival, so the observer waits a massively long time before stopping the program.
Mathematically, that means we push the stopping probability p closer and closer to 0.
And as p shrinks down to 0, that expression 1 over 2 minus p smoothly and inevitably becomes 1 over 2, exactly 1/2.
1/2. I want the listener to really visualize the physical reality of what we just proved here.
Let's do it.
This computer program is a physical switch. It flips to 1, it flips to 0. It physically cannot be anything else. It has never, in its entire infinite history, visited the coordinate 0.5.
Nope, never.
And yet, when subjected to a fair, randomized observer, the macroscopic expected state of this furiously flickering system is perfectly, rigorously 12.
It is incredibly reminiscent of quantum mechanics. A particle can be in a superposition of 2 discrete states, bouncing between them in a wave function. But the macroscopic reality we observe, the expectation value, is a stable point right in the middle. The STP operator is doing quantum measurement on pure arithmetic.
That's a perfect analogy. It shows that even a non-halting oscillating path has a deep, stable center of gravity.
It does. But Grandi's series is bounded. The walls are close together. The text doesn't let us get comfortable. It immediately escalates to a much more terrifying algorithm.
The unbounded alternating path.
Yes. This is where the devils really start to howl. The increments aren't just 1 and a minus 1 anymore. They grow. Add 1. Subtract 2. Add 3. Subtract 4. Add 5.
So the state space, the running total, starts doing these massive, violent swings. State 1 is 1, state 2 is -1, state 3 is +2, state 4 is -2.
It's swinging 1, -1, 2, -2, 3, -3. The pendulum is swinging wider and wider, tearing itself apart, heading toward positive and negative infinity simultaneously.
A classical mathematician looks at that and runs for the hills. The variance is infinite.
But we have our fair geometric observer. Let's stay calm and apply the coin flip. We want the expected state. Conceptually, how does the math handle this explosion? Because we can't just throw away the even steps this time. They aren't 0 anymore, they're large negative numbers.
Right. We handle it by splitting the reality into two halves. We create one infinite sum for all the odd steps, which are growing toward positive infinity, and we create a second infinite sum for all the even steps, which are plunging toward negative infinity.
Huh?
Each of these states is weighted by the tiny decaying geometric probability of the observer stopping the program at that exact moment.
It feels like trying to balance two exploding rockets.
It really does. But here's the magic of the geometric coin flip. Because the survival probability decays at a smooth exponential rate, it acts like a perfectly calibrated dampener.
Ah.
When you combine the positive rocket and the negative rocket, the terms almost completely cancel each other out. The positive 3 state is almost perfectly erased by the negative 3 state that follows it.
With just a tiny mathematical sliver left over, due to the fraction of a percent chance the coin landed heads in between them.
Exactly. The text walks through the calculus of this, utilizing the derivative of a geometric series. And instead of reading the algebra, I'll just say this. The infinite chaos collapses into a single, beautiful, closed-form fraction. All the massive swings cancel out, leaving a ratio where the top and the bottom both contain the probability parameter p.
And as we apply our fair observer limit, as we push p towards 0, forcing the observer to wait until the swings are infinitesimally massive.
The final expectation lands at exactly 14, 1/4.
A system whose partial states are whipping back and forth across the universe, an entirely unbounded chaotic algorithm, possesses a deeply stable, rigorously proven expected state of 14. The devils aren't just tamed, they are domesticated.
It is genuinely breathtaking that math works this way, but as deeply satisfying as it is to see the chaos resolve to 14, the text points out a subtle, lingering philosophical problem.
Yes, it forces us to pivot to the next major evolution in the framework, the problem of synthetic observation.
Right. We solved the problem, yes, but we solved it by cheating, just a little bit.
A little bit.
We used the geometric Stato P law. We introduced a memoryless coin flip. The parameter p was chosen by us, the mathematicians. We stood outside the mathematical universe, brought a loaded coin into the room, and used it to force the system to average out.
It is an artificial clock. It works perfectly, but it relies on an external synthetic intervention, which raises a profound theoretical question.
What if we don't invent the observer?
Exactly. What if we don't bring an artificial coin flip into the room? Is there an observer that is intrinsic to the mathematical universe itself? A clock built out of the fundamental, naturally occurring fabric of numbers.
Which brings us to the prime S-Sta-P law. This is the section of the text where computability theory suddenly collides with pure number theory. The authors construct an observer using prime numbers.
When I first read this heading, my jaw genuinely dropped.
Same. How do you construct an observer out of primes?
It's a phenomenal conceptual leap.
Yeah.
Instead of a coin flip with a fixed probability p, we build a scale-dependent observer. We choose a massively large-scale parameter, let's call it n, and we dictate that at every step of our computer program, the hazard rate of stopping the probability that the red button gets pushed is exactly equal to the density of prime numbers in the universe, up to that massive scale n.
Okay, I want to visualize this. Prime numbers are the atoms of math. 2, 3, 5, 7, 11. As you count higher and higher into the millions and billions, prime numbers become more and more rare, right? They spread out.
Exactly. The density of primes decreases as you move toward infinity.
So instead of a random coin flip, the probability of our program stopping is dictated by how crowded the prime numbers happen to be.
Yes, the text represents this stopping probability mathematically as the prime counting function, pi of n divided by n.
Now, before we can use this prime density clock, we have to audit it. We have to ask, does this natural intrinsic observer pass our 2 strict axioms for being asymptotically fair?
Let's test it. Condition 1, tail exploration. To be fair, as our scale parameter n approaches infinity, the stopping probability must approach 0. This forces the observer to wait a massively long time and explore the deep tail of the computation. Does the prime probability approach 0?
It does, because of the prime number theorem. The theorem proves that the density of primes is roughly equal to 1 divided by the natural logarithm of n. As n gets infinitely large, the natural log gets infinitely large, meaning 1 over that log approaches 0.
The primes spread out so much that the stopping probability vanishes.
Exactly. Condition 1 is mathematically guaranteed.
What about condition 2? Spectral non-resonance. Remember the strobe light? Our observer cannot have a hidden rhythm that phase locks with a periodic algorithm.
And this is where the choice of primes is so unbelievably perfect. Because if there's one thing prime numbers are famous for, it's their irregularity. They're fiercely aperiodic. There is no strict, repeating rhythm to where prime numbers appear on the number line.
They're the ultimate mathematical static.
Exactly. So an observer whose clock ticks are triggered by prime density acts like a beautifully irregular, stuttering strobe light. It flashes unpredictably. Because of that inherent structural randomness, it can never ever synchronize with a periodic, oscillating algorithm.
It effortlessly passes condition 2 just by the inherent nature of being prime.
It's so cool.
The primes naturally filter out any periodic noise. They are an intrinsically fair observer built into the bedrock of arithmetic. So the ultimate test. Let's take Grandi's series, our simple 1010 program, and reevaluate its expected state using this new natural prime clock.
We know from our earlier geometric calculation that the expected state of Grandi's series is simply 1 divided by the quantity 2 minus the stopping probability.
Yeah.
So all we do is swap out our artificial coin flip p and drop in our prime density probability.
The expectation becomes 1 over 2 minus prime density. Let's conversationally unpack what happens if we evaluate this. We can use the prime number theorem to substitute 1 over the log of n in place of the prime density.
So the formula becomes 1 divided by 2 minus 1 over log n.
If we factor out a 12, we can set this up as a standard binomial expansion. It becomes 12 multiplied by an infinite polynomial based on the log of n.
I won't list the whole polynomial, but let me synthesize the physical meaning of what expands out. The expected state still centers around our tamed, stable value of 12. But because we're using a natural clock instead of a perfect mathematical coin, the convergence isn't flawless.
It approaches 12, but it carries a very specific mathematical drag, an error term.
Right, and that dominant error term is exactly 1 divided by 4 times the natural log of n.
The error in our computational measurement is directly controlled by the spacing of the prime numbers.
But the text doesn't stop there. It asks a question that pushes this entire framework into the realm of the profound. It asks, what happens if we look closer at that error term?
What if we want a sharper measurement of the primes?
And this is the moment the text ties our simple, oscillating computer program to the most famous, elusive, unsolved problem in the history of mathematics.
The Riemann hypothesis.
I practically jumped out of my chair when I reached this section. How does the Riemann hypothesis enter a conversation about an infinite loop bouncing between 1 and 0? Let's unpack this slowly.
It comes down to how accurately we can describe the prime density. The prime number theorem gave us the approximation of 1 over log n. That's a good, smooth average. But prime numbers aren't perfectly smooth.
No, they clump up and spread out in subtle ways.
If we want a perfectly accurate clock, we need to account for that clumping. We need to map the exact wobble in the prime staircase.
The exact wobble, I like that.
And the Riemann hypothesis is essentially the master key to that wobble. If we assume the Riemann hypothesis is true, it provides a phenomenally tight, explicit bound on exactly how much the true count of primes deviates from our smooth logarithmic average.
It says the primes aren't just chaotic, there is a highly constrained, hidden order to their spacing.
And that hidden order, the exact fluctuation of the primes, is governed by something called the non-trivial zeros of the Riemann zeta function. You can think of these zeros as a set of infinite fundamental frequencies, like tuning forks.
So the prime numbers are laid out on the number line based on the complex acoustic interference of these infinite tuning forks.
That is exactly how analytical number theory views it. Now, bring that back to our computer program. If we plug this hyper-accurate, Riemann-backed prime probability into our STP operator,
our stopping clock is no longer just a smooth logarithm. It is now a highly complex mathematical gear vibrating with the frequencies of the Riemann zeros.
and when we run Grandi's series through that vibrating gear,
The error term, the exact rate at which our stopped computation converges to its stable answer of 12, is directly modulated by those tuning forks.
the convergence fluctuates in exact lockstep with the non-trivial zeros of the zeta function.
I want to just pause here. Let's really absorb the sheer magnitude of this connection. We started with a dumb, simple algorithm, add 1, subtract 1, a program so basic a child could write it in 3 lines of code.
Right.
But because it doesn't halt, we had to observe it. And we chose to observe it using a clock made out of the natural density of prime numbers.
And the consequence of that observation.
The consequence is that the tiny microscopic errors in the final output of our computer program are literally imprinted with the deepest, most heavily guarded secret of the prime numbers. The non-trivial zeros of the Riemann zeta function are dictating the computational physics of our divergent program.
It's like discovering that the dust motes floating in your living room are dancing to the exact rotational frequency of a distant galaxy.
That's a beautiful way to put it. It is the ultimate demonstration of the interconnectedness of mathematics. The artificial walls between computer science, continuous calculus, and pure number theory just completely dissolve. You touch an oscillating algorithm on one end, and the Riemann hypothesis vibrates on the other.
It is genuinely awe-inspiring. But knowing this text, as soon as we feel a sense of awe, it introduces a scenario designed to break the system entirely.
Of course it does.
We've tamed bounded oscillations, and we've tamed unbounded swings. But what happens if the path doesn't swing at all? What if it just runs away in one direction, accelerating forever?
Escaping paths and the need for renormalization. Let's set up the breaking point. Imagine a computer program whose incremental updates are simply the counting numbers, 1, 2, 3, 4, 5.
So the state space, the running cumulative total is 1, then 1 plus 2 is 3, then 3 plus 3 is 6, then 10, then 15. The states are the classic triangular numbers.
They're accelerating rapidly toward positive infinity. There is no oscillation, no minus signs to save us, no rockets canceling each other out. It is a monotonic explosion.
So let's apply our trusty geometric STP law. Our coin flip. We want the expectation, the infinite sum of the geometric stopping probability multiplied by the state n times n plus 1 over 2.
The text works through the standard identity for this sum, and it turns out the math doesn't magically collapse into a tidy fraction like 14. The expected state evaluates algebraically to exactly 1 divided by p squared.
1 over p squared.
Yeah.
Okay, let's apply our fair observer limit. We push the stopping probability p towards 0, forcing the observer to wait.
And what happens to 1 divided by a vanishingly small number squared?
It blows up. 1 divided by 0.0001 squared is a massive number. As p hits the infinite horizon, the expected state mathematically diverges to infinity.
It explodes. The algorithm has truly escaped. Our geometric observer, as powerful and fair as it is, cannot force this specific path to converge into a single finite number. The macroscopic average itself is infinite.
So does the framework fail? Do Abel's devils finally win?
Not at all. Infinity isn't a failure in this framework. It is a mathematical signature. It's a diagnostic label that says this path is fundamentally explosive.
But even within an explosion, there is hidden structure. To extract stable meaning from a process that is blowing up, the text requires us to borrow a heavy-duty technique from quantum physics, renormalization.
Renormalization. This is a concept that usually requires a PhD in quantum field theory to even approach. We need to build a really intuitive, concrete, mental picture for the listener. How do you extract a finite, solid number out of a mathematical explosion?
I like to use a visual metaphor. Imagine you are trying to observe a distant, incredibly powerful star. If you just open your naked eyes and look at it, you are instantly overwhelmed by an infinite glare of blinding light.
The light floods your vision.
Exactly. You can't see the actual surface or structure of the star. All you see is the blinding explosion.
That blinding glare is our 1 over p squared. It's the dominant divergent infinity that obscures everything else.
So what does an astrophysicist do? They don't just stare at the glare. They put heavily calibrated, mathematically precise optical filters over their telescope lenses.
Oh, nice.
These filters are designed to artificially peel away the overwhelming layers of blinding light, what we call the divergent bulk. And once you strip away the infinite glare, you can finally see the finite, solid, stable core hidden inside the star.
I love that. Peeling away the divergent bulk to see the solid core. Mathematically, how does the STP operator put on those sunglasses?
It uses a tool called a Laurent series expansion. We take our expected state, which is a function of our stopping parameter, and we expand it into a polynomial series. A Laurent series is perfect for this because it automatically isolates the different pieces of the explosion.
It separates the terms that blow up to infinity, the terms that vanish to 0, and exactly one term that is a solid, unchanging constant.
That constant term, the number sitting alone without any variable attached to it, is the solid core of the star. It's the finite truth left behind. The text calls this the renormalized residue.
It is the intrinsic value of the path, separated from the infinite glare of observation. But, and this is perhaps the most crucial, but in the entire text, the framework introduces a phenomenon called scheme dependence.
Scheme dependence. This is the idea that the finite truth you uncover depends entirely on the coordinate system your observer is using to measure time. The clock you choose alters the reality you find.
It is a profoundly relativistic concept. Let's explore exactly how this works by comparing two different observer schemes. The text labels them scheme alpha and scheme beta.
Let's start with scheme alpha. This is the coordinate system we've been using. Discrete probability. We measure time in discrete coin flips. Our stopping parameter is simply p, and we know from our calculation that the expectation of our exploding triangular numbers is exactly 1 over p squared.
Right, so if we write out the Laurent series for this expectation in terms of p, what does it look like?
It's incredibly short. It's just 1 over p squared plus exactly 0. There are no other hidden terms in the polynomial.
So we apply our mathematical sunglasses. We instruct our renormalization operator to peel away the blinding 1 over p squared term and look for the solid constant term that remains.
And what remains is 0. The renormalized residue in scheme alpha is a perfectly finite, solid 0.
Simple, clean, and rigorous. But now we change the clock. Let's switch to scheme beta. Let's suppose our observer isn't flipping discrete coins at tick-tock intervals. Let's suppose the observer's clock runs on continuous, fluid physical time. We'll let tick represent continuous time.
Okay, so we need to translate our stopping probability p into this continuous coordinate system. The text uses standard radioactive decay logic. The probability of the program surviving over a duration of time t is e to the power of negative t.
Which means the probability of stopping our new p is 1 minus the survival probability. So p equals 1 minus e to the negative t.
We substitute this new continuous time p into our expectation formula. Instead of 1 over p squared, we now have 1 divided by the quantity 1 minus e to the negative t squared.
And our goal is exactly the same as before. We want to find the Laurent expansion of this expectation as our continuous time t shrinks down towards 0. We want to peel away the infinite terms involving 1 over t squared and isolate the hidden constant term.
The text works through this continuous time power series division, and the calculus is gorgeous. It's like watching a master clockmaker disassemble a gear. We start by expanding the denominator using a Taylor series. The Taylor expansion for 1 minus e to the negative t starts as t minus t squared over 2 fin plus t cubed over 6n.
And because that whole term is squared in our formula, we have to mathematically square that infinite polynomial. It creates a massive expansion. The denominator becomes t squared multiplied by an infinite series of fractions.
Now, to get the expectation, we have to find the reciprocal. We have to divide the number 1 by this massive infinite polynomial. It's like sifting fine sand through tighter and tighter meshes. We set up an equation with unknown coefficients C0, C1, C2, and we start matching them up to force the whole thing to equal 1.
As we sift the sand, the explosive infinite terms fall out first. The 1 over t squared term drops out. Then the 1 over t term drops out. And then finally, we isolate the C2 coefficient, which perfectly aligns with our constant Fulchen to the power of 0 term.
The final fraction that slips through the mesh.
And what is that constant term in scheme beta?
The calculus spits out exactly 512.
512.
Yeah.
Okay, I have to stop the deep dive right here because the text anticipates this exact reaction, and I felt it in my bones when I read that number. 5/12. Anyone who has watched a single YouTube video on advanced math or read a pop science article about string theory knows about the infamous zeta regularization result.
Of course.
The sum of all positive integers, 1 plus 2 plus 3 plus 4 to infinity, is notoriously magically equal to negative 112.
It is one of the most famous and baffling counterintuitive facts in mathematics.
Exactly, negative 112, not 512. So when I saw 512, my first instinct was the STP operator is broken, the fair observer failed. It gave us the wrong answer to the most famous divergent series in the world.
It is a deeply visceral reaction. I felt the same thing. But the STP operator isn't broken. It is doing something incredibly subtle and profound. And understanding why it outputs 512 instead of Angus 112 is the absolute crux of Section 7, the physics of computation. It resolves the paradox entirely.
Yes, let's play detective here. We need to find the discrepancy. Where did the missing fraction come from? Because mathematically, 512 is exactly equal to negative 112 plus an extra 12. Where did the extra 12 come from?
To find the missing half, we have to look exactly at the mechanical difference between what the classical zeta function is measuring and what our observer is measuring. The classical zeta regularized series takes the raw integers, the number k, and multiplies them by a smooth decay function, e to the negative tk. If you run the Euler-Maclaurin expansion on that smooth series, the constant residue is indeed flawlessly negative 112.
That is the mathematical baseline, the pure sum of integers.
But look at what our STP observer is actually doing. It isn't evaluating raw integers floating in vacuum. It is evaluating the partial states of a computer program, S-tau. And logically, what is required for an observer to read the increment at step k?
To read step k, the program had to survive step 1, step 2. It had to survive up to step k minus 1.
Ah, the survival weights are shifted. The probability of evaluating the KO state relies on the survival probability up to k-1. In continuous time, that survival probability is e to the negative t multiplied by k-1.
The observer introduces a microscopic offset. Because it is evaluating a sequential path, the exponent has a -1 in it, and mathematically, e to the power of negative t times k-1 can be factored. It factors out into the standard e to the negative tk multiplied by an extra floating factor of e to the positive t.
The STP operator inherently injects an extra factor a to the d into the entire computational system just by the physical act of observing a sequential process.
And when you multiply an infinite polynomial by e to the t, well, we know the Taylor expansion for e to the t is 1 plus t squared over 2 phi. When you multiply that exponential shift against the classical zeta polynomial, the cross multiplication takes the explosive 3 squared term from zeta, multiplies it by the e squared over 2 phi from the observer's shift. The t squares cancel out, leaving exactly a constant of 12.
The physical necessity of surviving the previous step perfectly translates into a mathematical shift of 12 in the final renormalized residue. Negative 112 plus 12 equals 512. The STP operator wasn't wrong. It was precisely measuring the physical burden of sequential survival.
It is flawless. The discrepancy isn't an error. It is the physical footprint of the observer. And the text doesn't just ask us to take their word for it on one example. They provide rigorous evidence in the exercises at the end of the chapter to prove this exponential shift is a universal law of this framework.
Yes, let's look at the exercises dealing with quadratic paths, the sum of squares. This completely cements the idea.
Let's look at the alternating quadratic path first. 1 minus 4 plus 9 minus 16. The text asks for the expectation under the discrete geometric S-to-Ho P law, and the answer provided proves that as P approaches 0, the expectation collapses perfectly to 0.
Which perfectly aligns with the classical Abel sum for an alternating quadratic series. Theta of -2 is exactly 0.
Right. But then the text gives us the non-alternating quadratic path, the escaping sum of all squares. 1 plus 4 plus 9 plus 16 to infinity. Classical zeta regularization proves that the sum of all squares, zeta of -2, is strictly 0.
But we aren't using pure zeta. We are using our continuous time continuous observer. What does the STP operator find?
The exercise asks us to find the Laurent expansion for the continuous time expectation. We go through the exact same power series division. We divide the infinite polynomials, sifting the explosive sand, and the crucial equation that isolates the constant p to the power of 0 term spits out exactly 13.
The renormalized residue of the squares under continuous observation is 13, not 0.
And once again, we play detective. Where did the 13 come from? We take the classical zeta series, which has a constant term of 0, and we multiply it by the observer's exponential weight shift, e to the t.
The zeta polynomial for squares starts with an explosive term of 2 divided by t cubed. When you multiply that 2 over t cubed by the t cubed over 6-foot term from the e to the t expansion.
The t cubes cancel out. 2 multiplied by 16 is exactly 26, which simplifies to 13.
It matches perfectly every single time across different algorithms. The discrepancy between the classical pure math and the STP operator's output is exactly the physical contribution of the observer's survival shift.
This brings us to what I think is the most profound synthesis in the entire text. It is a grand analogy that redefines how we should view math. Renormalization residues are coordinate dependent.
That is the ultimate takeaway. The finite truth left behind that solid core you see after peeling away the infinite glare of the star is not an absolute static number floating in the void. The truth depends on two interacting things, the mathematical path itself and the coordinate system of the clock observing it.
How you measure time physically alters the finite residue of an infinite explosion. Discrete coin flips give you 0, continuous clocks give you 512, and neither of them is wrong.
It is a stunning, rigorous, discrete analog to one of the most complex ideas in quantum field theory, renormalization group flow. In quantum physics, physical parameters like the mass of an electron or its electrical charge aren't absolute fixed numbers. They literally shift, grow, and flow based on the scale at which your instruments observe them. As you zoom in closer to an electron, the cloud of virtual particles in the quantum vacuum changes your measurement. The reality is scale dependent.
So what this text has mathematically proven is that computational algorithms possess the exact same quantum physics. Divergent series aren't just abstract logic puzzles that went off the rails. They are dynamic physical systems that respond to the observer scale and coordinate framework.
Abel thought divergent series were the invention of the devil, because they seem to give shifting, paradoxical answers depending on how you looked at them. Euler thought they held the true shape of the infinite, but he didn't know how to compute it without cheating. The STP operator is the ultimate synthesis of both anxieties.
It shows that Abel's shifting answers weren't fallacies or tricks. They were physical coordinate transformations. They were the math trying to tell us that reality is relative to the observer.
The STP operator truly is the Exorcist. It tames the devils, not by erasing the chaos, but by making the observation process mathematically explicit and rigorously fair.
As we step back and reflect on this deep dive, it is amazing how drastically our mental models have shifted. We started this hour with the spinning beach ball of death. We assumed that an infinite loop was a broken computer program, a dead end, a non-halting error that had to be force quit and discarded.
And we arrived at the realization that divergent series are just computations that never halt, observed through asymptotically fair stopping processes. They aren't failures. They have robust expected states. They have geometric equivalents to classical damping. They have intrinsic prime architectures vibrating with Riemann zeros. And they possess coordinate-dependent renormalized residues that mirror quantum mechanics.
It makes you wonder what other inherent stopping laws exist out there in the mathematical wilderness. What other clocks can we use? The text hints at this potential in the exercises, where they introduce a Poisson distribution for the stopping time.
Right. The observer pulls a random stopping time based on a Poisson decay parameterized by lambda. And as you push that lambda to infinity, the stopping distribution acts as a hypersmooth filter over the partial states, mathematically matching something called Borel regularization. It just proves that this framework is infinitely adaptable. Any probability distribution that obeys the rules of fairness can act as a valid observer, extracting a slightly different mathematically valid slice of truth from the infinite path.
It completely dissolves the boundaries between disciplines. An executing line of Python code, a prime number, and an electron are all subject to the exact same physical laws of fair observation and scheme dependence.
It is moving toward a unified theory of the infinite.
It really is. And I want to leave you, the listener, with a final provocative thought to mull over as you go about your day, something that builds on everything we've uncovered today.
Let's hear it.
Think back to our opening metaphor. The frustration of the frozen computer, the expectation of clean, absolute binary engineering precision. We spent this entire deep dive proving that in the purest realm of mathematics, the truth of an infinite exploding process is an absolute. It changes depending on the specific mathematical clock you use to observe it. Whether you use discrete coin flips or continuous radioactive decay, your finite reality literally shifts from 0 to 512 to 13.
The residue of reality is inherently coordinate dependent.
Exactly. So my question to you is this. If the ultimate foundational mathematical truth of a process is completely dependent on the observer's clock, what does that say about the final states of the actual physical processes happening around us in the universe every single day? When we measure the mass of a star or the behavior of a cell or the trajectory of an economy, are we really seeing the absolute fundamental reality of the universe? Or are the physical laws and constants we observe just the highly specific finite residues of our own human coordinate system? Are we just the STP operator for our own reality, blinded to the infinite paths running right past us?
That is a thought experiment worth holding on to.
Until next time, keep diving deep.